Okay, so what's the outline for the semester? So the syllabus that you all picked up gives this to you, but I want to actually talk about it. Oh. Everybody got this? So we're not following the order of the book at this point. We're doing chapter 7 first. You will thank me later. So we've done all the derivative story. Now we have to do the integral story. And so we'll talk today about what integrals mean, and we're going to do a lot of physics applications here. So not quite so many physics people, but still I think it's good for everybody to see some of the applications. So then what do you expect to come from what you did in single variable calculus? Once you learned what the integral was, what came next? No, that came first.
Applications.
Well, it came early in single variable. Once you know what the integral in terms of Riemann sums, what did you learn next?
Washer and
Fundamental theorem.
Before you started doing volume application,
Fundamental.
fundamental theorem, which ties
yeah.
together derivatives and integrals. That's the whole beautiful theory there. So that's where we're headed next. So chapter 8 is integration on manifolds. There's that dreaded word again. So we're going to do integrals on curves, integrals on surfaces, integrals on manifolds in general, and then the theorem that ties together the derivative with the integral is the fundamental theorem of calculus, which becomes something that some of you have heard of called Stokes' theorem, spelled correctly. So that is the crowning theorem of the course, but it's not the end of the course. So what do we have to do to get from here to here? We have to go back and actually talk about manifolds a little bit more. So now we go back to chapter 6. So we finally will do the inverse function theorem, which you've heard of. I talked about the implicit function theorem. And we'll talk more about manifolds. So we're ready for this. And then the end of the course is the end of the linear algebra story. But we'll tie it in with this stuff as well. So we're going to talk about eigenvalues, eigenvectors, whatever those are, diagonalizing matrices, and a whole pile of applications. So we'll talk some about differential equations. We'll talk some about Markov processes. And then I'll talk a little about complex numbers and how that stuff ties in. And I'll also try to connect this stuff up with this a little bit. So the linear algebra will appear also a little bit here. We'll talk about determinants some more, finally. You asked about those a lot last semester, so they'll come back here.
What's the DE at the end there?
Differential equations.
Okay.
So this is the intro to 4700. So several of you have had 2700, like 5 of you maybe? Is that all? Maybe some of the people that we lost had it.
I'm taking it.
Okay. So we're going to do some of the overlap with 2700 and get ready for 4700, which is the 4,000 level course on differential equations, systems of differential equations. So the warning here is that integrals are harder than derivatives. Remember that problem from calculus? So it's true here too. You are going to have to review your Calc 2 and integration technique some. I expect that on some of these problems, you'll get to a point where you're using Wolfram Alpha or Mathematica more. Will, is your Mathematica still alive?
I believe so.
Patrick, what about you?
No.
No, so remind me to put you on the list when I send for new ones. Okay. Any questions, any comments?
Wait, will Wolfram Alpha be necessary to calculate, to like perform an integral, or will?
I mean, every problem I'm going to give you is doable by hand, but there may come a point where you get sick of doing integrals and want to get some computer help. You're still going to have to do the setups. That's the hardest part here, is setting up the integrals and setting up. As you're going to see by the end of the week and the beginning of next week, there's an art to actually taking regions in 3 dimensions and figuring out how do I integrate over them. I have to visualize things well enough to actually set up one-dimensional integrals out of them. So once you've got to that point, you can feed it into Mathematical. But I would, again, like as I did last semester, encourage you to do enough by hand that you know what you're doing. And then once you basically say, okay, I know what I'm doing, I don't mind you're using, for web work stuff, I don't mind you're using technology to save time. Okay? All right. So, what is integral anyway? No.
Area under a curve.
Area under curve. It's not the same thing. That's the fundamental theorem of calculus. How many people remember how an integral is how many people remember how the integral is defined?
Didn't we do that soup of, well, no, that was for curve length.
Well, but it's analogous to that.
Isn't it like taking like little divisions and finding the area underneath?
So if you had a function that isn't necessarily continuous, but let's say is always greater than 0 or greater than or equal to 0. And suppose I wanted to define the integral of the function from a to b. How did you set that up?
It's the limit of an infinite sum, or the limit of a sum.
The limit of a sum is the way most people have been taught it.
It's the soup of the lower, if you partition it, limiting out to infinity, it's the soup of the lower.
No, don't mention any word with infinity. So again, you want to think of approximating area. This goes back to Archimedes, who knew more calculus than you guys all realize. But he had these ideas. Divide the interval AB up into pieces.
And the soup doesn't have solve the sums.
And they don't have to be equal pieces. What do you do once you have these pieces? You want to approximate the area. So what do?
You go up to f of x. On the
Well,
value.
where do I go?
Take the lowest
Since you're
point.
using the
Doesn't
right,
matter.
left.
Yeah, so I'm not going to do right and left, but what I am going to do is take biggest and smallest. So this is not how everyone was necessarily taught, but the 2410 people had it this way. And this is how we're going to do it. And on each interval, you're going to take the max of the values, or the soup, because there may not be a max. And you're going to make a rectangle with that height. So here you would have, on this next interval, you would have this. Whoop. And then you would have here. And then you would have here. Whoops. And then you would have there. And then you would have there. I made too many pieces. And then you would have here. And you would add up these areas. And that would obviously be an upper estimate on what you're trying to compute. You then come along and you do the same thing on the lower side, and you have inscribed rectangles here, if you like. On this piece, whoa. I seem to have a little bit of a, I don't know, this looks like it ought to be here. And then here. Here, and then here, and then here, and then here. So I would add, yes sir?
What's the opposite of soup? Like, how do
inf. So I'm going to write all this stuff down carefully in a minute. So what you start with here is a partition. So be patient, Justin. I'll actually write out definitions for two variables. So I'm starting off with a partition of the interval a, b here. And then to that partition, I associate to each piece, I associate the height of the circumscribed and the height of the inscribed rectangles. So you would have capital MI would be the sup of the values f of x when x is in the ith red piece interval. And little mi would be the inf. So remember, sup is like max and inf is like min. And then you want to consider what's called the lower sum for that partition, where you just add up the pink areas. So that would be add up the heights. So on the ith piece here, for example, this is the ith piece, you would take, you would go from ti minus 1 to ti, but I'm not going to make a big deal out about that. That would be the length of the interval times the height of the rectangle, so that's the area of the rectangle. And then you would analogously do the upper sum, where you do the exact same thing with the big M's. So that's an overestimate, that's an underestimate. And then what do?
Make them with an epsilon or each other.
You hope you can,
Yeah.
right? And so what you would say is that the integral exists if there is a unique number. This is different from what you were taught last year, but it's equivalent. If there's a unique number, I, that's between all lower sums and all upper sums. So if there's a unique number that's between the underestimates and the overestimates, that's called the integral. And that idea has the obvious properties that if you had one f that was bigger than another f, then the area under the bigger one would be at least as big as the area under the smaller one, which is one of the key ideas you want to have. Now, it was very vague here. This is not official. I didn't say anything about what f has to do. Any properties you think I have to know for f in order to even make sense of any of this? So here I have a function on an interval to the real numbers. Certainly doesn't have to be continuous. But what, for these things to make sense, what do I have to stipulate about f?
It's defined.
Well, it's defined.
Does it have to be bounded?
It has to be bounded. Right? It can't go off to infinity or else this won't make sense. You have to actually have a sup value. It can't be blowing up. So you have to assume that f is a bounded function both above and below. And then all of this makes sense.
Well, if f is defined on a closed interval, it...
Only if it's continuous.
Oh, right, okay.
So I'm not stipulating continuous, and in fact, a lot of applications it won't be continuous. Okay, so what we want to do is tool up for this to do the analogous question now in more variables. So you want to, instead of doing area under a curve, what do you want to think about if you had a function of two variables? You want to think about volume under a surface above the xy plane. So now you want to think about pictures like, so let's now start with the official definition. If. Patty, how am I doing on size?
That's fine. I can zoom in, so.
say, a double, or in more general dimensions, a multiple integral. So we're going to do this in baby steps. Today we're going to talk about rectangles, and then tomorrow we'll talk about how you would integrate over things that aren't rectangles. So let's let R be a rectangle in the plane. So now I have to draw 3D pictures because I want to talk about a function. This is terrible notation, but live with it. Right? F is mapping the rectangle to real numbers. And it's going to be a bounded function. So again, remember that just means that the values of the function form a bounded set. So here in my picture now, we're going to have a rectangle with its sides parallel to the axes. So here's my R. And you have a function whose graph I'm going to try to draw. It doesn't have to be continuous, it just has to be bounded. But I'm not going to try to draw something totally ridiculous because the art is difficult enough when it's not totally ridiculous. So over this rectangle, you can imagine some sort of flying carpet shape. And that represents the graph of the function over that rectangle. Okay, so this would be z equals f of x when x is in the rectangle. And I'm going to do the same thing to you this semester as I did last semester. I'm going to use x for a vector, and then I'm going to call its coordinates x and y. You're welcome. So I'm interested in saying what's the volume under this surface and above the plane z equals 0. And again, you're going to do the same game. You're going to chop the rectangle into pieces. So you're going to start with a partition. So you're going to form a partition P of the rectangle by partitioning, as we did in that picture. You're going to partition the interval from A to B, and you're going to partition the interval from C to D. So you're going to divide this up into some number of pieces, not necessarily even. You're going to divide this up into some number of pieces, not necessarily even. And then you're going to make a crisscross pattern. So if I draw the picture without the silly perspective for a minute, here's R, and I'm picking 3 pieces for this interval here, and I had 4 there, right? My picture's not quite to scale. And then you just literally form rectangles by using all those dividing marks. So by choosing officially I'll call the x division points x sub 1 up to x sub k, and in the y I'll call them y naught up to yl. So these points here are the x sub k's, x sub i's, and these points here are the y sub j's. Mm-hmm.
The partitions always has finitely many parts, right?
Yeah. Nothing infinite going on. Okay? So you then would have for each I between 1 and k, you can see the notation starts to get to be a pain in the butt. And so we're going to try to dispense with the pedantic notation as quickly as possible, but I have to do it to get us started. So here, these are my x sub i's, and these are my y sub j's. here, and I get the ij rectangle by being the ith interval on the x direction and the jth interval on the y. So this reminds you of what? This notation.
Matrices.
Yeah, it reminds you of matrices. So for each, consider r sub ij, which is the interval xi minus 1 to xi, cross the interval yj minus 1 to yj. And so you've divided your blue rectangle up into pieces here. And I'm taking a typical such piece. And I'm going to say, okay, let's approximate how much volume is under here in this little piece. Well, I'll take the highest mark over that piece, and I'll take the lowest mark over that piece and make boxes with those heights. So analogous to that picture, I'm not going to try to draw as much as I do there, but analogous to that picture, you would have, from the high mark, you would have a box that looks like that. Oops, I screwed it up. No. Patty's making me nervous. So you'd have a big box there, and then you'd have contained in there the low mark for that height, the low height, and you'd have an inscribed box there. So for each, consider Rij, and then you say, as we were doing up there, little mij is the minimum or the infimum of the values of the function on that rectangle, and big mij is the soup. And you add them up. So the lower sum, exactly analogous to what I was doing in one dimension, adds up over all these rectangles, the inscribed volume, and the upper sum adds up the circumscribed volumes. You can start to see now, if we were doing this in 3 dimensions or 4 dimensions or 5 dimensions, that this notation just gets to be obnoxious. So you can conceptualize that if you're in 5 dimensions, you divide each of the 5 intervals up, and then you need an index for each one. So it's now instead of having 2 indices, you'd have 5. What we're going to do, and not try to write down stuff like that other than in 2 dimensions, we're just going to say, do it, and then put 1 index there that counts them all. We're not going to try to write down indices once we get past this. So you do the circumscribed, that's the upper sum, and then the definition is, we say, f is integrable. So this is a function now that was defined specifically on the rectangle. So we say it's integrable, meaning on the rectangle, if upper sums and lower sums are getting better and better approximations for some number that ought to be the integral. So if there is a unique, so this is a critical thing, I, so that, exactly what I wrote up there, lower sum less than or equal to I, less than or equal to upper sum for all partitions.
What do you mean unique in this sense?
I mean, there's only one number that fits in between. So we're now going to do examples for the rest of today.
Why do we use that instead of like a standard epsilon definition?
Actually, that's not the definition, that's a theorem that we're going to prove. So we'll do that, I'll state that tomorrow.
So this is the definition,
This is the definition,
like,
like one of the things that you would know for the farm.
yeah, just the bottom part.
Yes. I mean, this is all notation that
All right.
defines this, but I'm not gonna say you need to write out the notation every time you say you know what integral is.
That's, I'm thinking things like in terms of the final.
Oh, please, Jonathan. We say I is the integral of f, and we write that integral of f dA over R. So the A is suggesting area, because you've chopped the thing up into areas. If you were in higher dimensions, in dimensions 3 and greater, which we will get to soon, we will write integral of f dv, v for our volume. And now you can complain that I'm not distinguishing, is it 3-dimensional volume, 4-dimensional volume, 5-dimensional volume. If we're in a situation where it's ambiguous, I might remind you with a subscript to say what dimension we're working with. All right, so what I want to do now is talk about examples, just to get us moving on this. Okay, so give me the simplest function you can think of.
Y equals C,
Not y,
Z equals C,
f of
F of X, Y equals C.
constant function, thank you. What do you think? Is it integrable or not?
Yeah.
Yeah.
What should its integral be?
Times
C times the area of
constant.
C times A minus B.
C times A.
What do you want to say?
C times
B minus
the
A.
area of the rectangle. Okay, so let's call that example 0. Let's let f of x be a constant c. Then you guys are claiming that the integral is c times the area of R. How are you going to convince me that it's correct?
Well, the lower the upper is always the same, so there's gonna be one number in that.
There you go, exactly right. So no matter what partition you take, good Cameron, for every partition, no matter how you chop the rectangle up, no matter how you do this, every one of these guys is to C. And every one of these is C. So when you do this, this is a C for all of them. So what can you do?
Pull it out.
Pull it out and use the distributive property, right? So no matter what partition you take, every Mij and capital Mij is equal to C. Therefore, every lower sum is the sum of C area Rij, which is C times the sum of the areas. And if you add up a finite number of areas of rectangles that filled up your big rectangle, you've got the area of the big rectangle. And likewise for the upper sum. Therefore, exactly as Cameron said, if these two numbers are the same for every p, there's only one option for I. And it's clearly unique because there's only one number between C times area of R and C times area of R. All right, let's get a little more adventurous. What about the function that is 1? Well, there's going to be a bunch of these, but yeah, let's say you're at the origin and it's 0 otherwise. let's say the rectangle is, just say, to make life easy, the unit square, the standard square. So you have a function on this standard square, and the function is 1 at this point, but it's 0 everywhere else.
Oh, it's in a row.
So what would the graph of this function look like, by the way?
Take the point and then
There you
zero.
go, right. So the graph, if I were going to graph this, here would be my square. And the graph of the function would look like dot over 0, and then flat surface everywhere else with a hole there. And of course, if you ask Mathematica to draw that, it's not going to draw you much. What's the vote?
No.
1 no.
No for what?
Is it integrable?
That's it.
Yes.
How much volume is under this surface?
It depends on
Zero.
the issue you take.
None.
Zero. It
None,
exists.
because there's no
Zero.
area.
If it exists, it's 0. So the question is, does it exist?
Well, I can draw you an infinite of partitions that's not zero.
That's true, you can, but that's not what the definition said. I never said that these numbers had to equal I just said it had to be the unique number sandwiched between them all.
There is enough of partition for widgets.
No, no.
There's not a unique number.
But it can get infinitely smaller sandwiches.
Well, it's not.
Yeah, I mean, I don't like using the language of infinitely small or infinitely large,
Very
but
small.
your intuition is correct. Justin?
Because the partition that includes the 1 dot is gonna have 1 all the way up at 1 and then 1 all the way down at 0 and then you can have anything in between.
But if you
Yeah.
make, could you make a partition just the line at equals
So
0?
my rules are my rules. So how do you want me to make a partition here? How many divisions should I make here? So we could do a partition where we divide up point here, and then we go to 1. And we could do the same thing on the y-axis, could we not? Single point, and then go to 1. So the rectangles now look like this, 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 and the big one.
The only one which isn't 0 is the possible one.
So first of all, so for any partition,
The lowest.
I just drew you this picture, but for any partition, which rectangle is going to, well, first of all, what are all the little m ij's?
Equals 0.
They're all 0. Everybody agree? For any partition. Because the function is 1 at this point, but it's 0 everywhere else, so no matter how I pick the rectangle, the inf of the values is 0. On this rectangle, the inf is 0, and on all the others, it's always 0. And what do we know about capital Mij's?
It's always possible.
It's 0.
The area of,
No areas. This is the values of the function.
It's 0 everywhere, but maybe in the bottom one.
So the very first rectangle, when both I and j are 1,
Yeah. It will always be.
you'll get a 1 there. When I and j are 1, and otherwise,
0.
right? Because except in this first rectangle, the function's dead 0. So the soup is 0. So what are the lower sums going to be?
0.
And what are the upper sums going to be? No.
Small, less.
No, I want a formula. What is the upper sum of f for any partition?
Area of R11.
area.
Area of R on 1. Right, there's the capital Mij, there's the area, and all the other terms in the sum are 0 because the capital M's are 0. So you say to yourself, glad you didn't forget that over Christmas. What number satisfies this for all p?
0.
No, there isn't one because if you make the make it just one whole partition of the entire rectangle, it's gonna be 1, right?
But that
No,
still
because you can
works.
have arbitrarily small,
No, you're right, Reese. So this number could be as big as 1, or as small as what?
Epsilon.
1 over infinity.
it can't, there's no number it's as small as.
That's right.
Yeah, there's no bounding law.
But by choosing this first rectangle to have as little area as you decide you want it to have, you can make this area as small as you want. So 0 satisfies this. And I'm saying it's the only number that does. Gabe,
No, it's just,
you're just resting, okay.
It's like an open ball, you keep getting closer.
So I'm claiming moreover, and is the only value that does. If you picked another number like 0.00001 for I, would this hold?
No.
Because you could do what?
Find a small enough area, that was, the
You
area
could
was
make
less
this
than
smaller than 0.00001 by choosing the right partition. So 0 is the only number that fits for all partitions. Therefore, f is integrable, and the volume is in fact 0. All right, well that was too easy. Ken, you gonna tell me what I'm gonna write this time?
Rational.
Oh, there you go. So if x is of the form where both x and y are rational, let's make the function be 1. And if otherwise, let's let the function be 0. You might not guess my next example.
what's that symbol? I'll be sh-
Oh, this?
Yes.
Rational numbers.
I mean, what? Is it
Old
like,
cube.
It's a Q.
okay, it's a Q with the two.
It's a Q with a bar in it, like the R and the Z.
It's also no longer script 2.
Now, that's not a script Q. This is the Q for rational numbers. Script Q is different.
Q script looks like a 2, right?
All right. So, for example, I could write this as x in Q2, like we write R2. This means it's rational in both coordinates. All right, so what does the graph of this function look like?
A mess.
A mess. It's got lots of dots up here and lots of dots down there.
I'm gonna vote no again.
Going to be right this time?
I sure hope so.
So yes.
I really think I'm right, but there's no.
Yes.
Who's saying yes? What are you saying yes to?
Because in virtual partition, you have highest point and the lowest point will be 0.
And what about the highest?
The highest will be 1.
For every rectangle.
Yeah.
I don't think this is gonna work.
I don't think so either, because I
can't-
feel like you
you're
could
either
pick a
gonna get one or zero.
rectangle square where there's only 0
Every
dot.
rectangle
so
has
your
irrational
I
and
will be-
rational points.
Right.
Right.
So every no matter what partition you take, every rectangle in it
We'll have a rational.
will have a point in it where the function's 1, and a point in it where it's 0.
Then
So what are all the big MIJs?
1.
What are all the small MIJs?
0.
So what's the lower sum and what's the upper sum?
0
Zero
and area.
and
Yeah, so if we're still on the unit square,
1. 0.
0 and 1. Is there a unique I? I'm going to write some of this down. Is there a unique I that's between 0 and 1?
No.
1/2?
Is that true? You can draw a triangle that has a rational number in it?
So you're actually going to have to think through this kind of stuff for some homework this week. But let me talk about that for a second.
Everything above it is irrational.
Think about like digital expansions. You know, you can, if you do have like.
All right, so the observation here, and Jonathan's asking for a little detail, I think.
Because every.
Yeah.
For any partition,
Irrational, yeah.
p, little mij is 0, and big mij is 1 for every I and j. Is he, all right, so I'm gonna ask for louder mumbling in a minute. Therefore, LFP is 0, and UFP is 1, so I'm doing R being the square again. For every P. And so we all agree that there's no unique real number between 0 and 1. So finally Cameron was right.
You mean again, Cameron was right.
Say finally.
Example 0?
Therefore, F is not integrable.
Do you mean R1 to,
Right, so this is area 1.
do you mean 1, 0 by 0, 1? You have 0, 1 by 0.
Yeah, that's what I meant. It's the same square I was drawing there,
Okay.
right? X coordinates go from 0 to 1, Y coordinates. All right, so now Reese is asking a question. Or was it was Jonathan? Who was it? It was Jonathan.
Yeah.
If I take any interval of real numbers, why is there a rational number in there? And why is there an irrational number?
Yeah.
Well, I've been saying if the,
The real numbers are continuous.
well, I was saying you could take the right endpoint and just truncate its decimal expansion if it was irrational and get something inside that was rational.
So if you think about real numbers as infinite decimals, that's a valid argument.
A long convoluted argument using root 2, the irrationality of root 2.
Well, that's, hang on, so the fact here is every interval in the real numbers contains infinitely many rationals and infinitely many irrationals. Rationals and irrationals. Without thinking about decimal expansions, can you give me an argument to get a rational number in there? Remember, what if A and B are weird numbers like E and pi? Does this interval have some length?
Yes.
Yeah.
It has.
Give me a random number for the length.
7.
That's pretty big.
You said right.
0.7.
If this interval had length 7, what kind of numbers for sure could you find in the
Maybe at
interval?
least 6 integers, right?
Integers. But use that same reasoning. Suppose the interval had length 1/7.
You could find tenths in there.
Then if I took the multiples of a tenth, there'd have to be one in there.
And you keep doing that for each.
Yeah.
Do you see why that's right? So you're going to have to write out an argument like this in homework for something that isn't quite the same.
That's just as a rational interval. So then
No, any length that's positive, you're going to be able to find a 1 over n that's less than that length.
No. So we have multiple rationals. How do we get the-
How do you get the irrationals? Can you tell me, can you convince me that between two rational numbers, there's an irrational?
Yeah.
What about between 0 and 1? Is there an irrational?
Square root 2 over 2 and multiply by 7.
So in there is 1 over square root of 2. And if you rescale this interval to that interval of rationals, if you write down the arithmetic for that, where this guy goes is going to have to be an irrational.
Really?
Because you
Don't do that.
Because you're just dividing the rational by, right?
So take the math that scales this interval and moves it around to get to this
Oh,
rational.
rational boundaries.
Rational.
Rational.
Right.
Okay, we're done for today. I'll be around this afternoon if you